Before I give a glowing introduction of Ian, I'm sorry we started late. That's why we don't have long for questions and statements. Had I known, had Ian told me that he didn't have a computer, I would have nipped up the road and got my computer. But I didn't know, so I'm terribly sorry. But we entertained you, didn't we?
We got a bit later though, going 6:15.
No, we'll see, all right? What I want you to do is, when you put your hand up, is give me your first name. I'll put your name down on a list, and believe me, you'll get a turn, all right? If we need to go over, because everyone's so excitedly interested, then I'll put it to the meeting if they want to go over a bit over 6 o'clock, all right? We have a nice meal. We ask you to donate towards the meal, $5 if possible. We'll accept $3 if you're broke. So, put up your hand if you want to ask a question. You were first with the orange. What's your first name?
Michael.
Michael. Professor. Brian. Who else? Abi. Okay. Anyone else? You can still put your name up, your hand up, but when your turn comes, but when you put your hand up, give me your first name.
Can I pass around a request? If you'd like to go on a mailing list for future talks like this, just give me your name and email address and I'll let you know. So
are there any non-members here? All right. Do you want to become a member? Put your hand up. Okay, we'll give you a membership form. Usually, if you get the Viewpoints, which is our magazine, if you're a member, which is this, that's where you're told. That's where you're told about which talks are on. Okay. All right. The first question is from Michael.
Okay, just on that last point about the expanding universe, if it's continually accelerating, then the basic particles of space are flying apart faster and faster.
Yes.
So it seems to me if they fly apart fast enough, then matter and antimatter may not annihilate because they'll be going apart from each other too quickly. And so therefore it could perhaps lead to the formation of matter and then collapse the universe again. So I just wondered if you had any thoughts about that.
Okay, I don't quite understand how them receding from one another can increase their interactions.
So that's how the inflation model works in the first place, is that the original baryogenesis of the universe is caused by things inflating and flying apart so quickly that matter and antimatter become separate from each other.
All right. I don't know. I can take that on notice. Yeah.
All right. Yeah.
Good question.
Okay. Before I introduce ask anyone else to, I'm sorry, I promised to introduce you. IBryce is our new president, and he is a qualified aeronautical engineer, hence he knows so much about these things, and now is part of our ethics classes in schools, voluntary program, and he teaches ethics in schools. Okay, the next person, Professor?
I just want to make a little comment before the question. The comment may be to say that unlike religion, science doesn't require you to believe in it for it to work. Even if I don't believe in science, my mobile phone will work. Whereas in faith, they always want you have to believe in our faith. Then only you get the return. So that's one point. My question really is, why is it that Homo sapiens have come with this notion of a God? In all ancient civilizations, they have come up with this idea of a God. Is there something that science can tell us about our brain, in that you know, the civilization in Central America, civilization in Asia, they all come up with this notion,
yes.
and is there a science-based answer to that?
Well, it's more into psychology than science. But yes, I have a simple explanation that religion had survival value. For example, imagine you're a tribe in Africa, and you're the king of the tribe, and there's another guy who would like to be king of the tribe also. King's the wrong term. What's the leader of the tribe?
Chief.
The chief of the tribe. Another guy wants to be chief, and he knows that he can sneak into your teepee or into your house at night and stab you, then he'll be chief. But if you can convince him that you've got an invisible being look after your back 24/7, then he's going to be a lot more scared to do it. So telling the others that there is a God and that you're his messenger is a very great survival value. So I would say that all of these things had survival value, and that's why they became known.
Okay, Brian.
Yes, thanks. The speed of light is at 300,000 a second in a vacuum.
Stand up,
Yeah,
they
okay,
can't
no.
hear you.
The speed of light is 300,000 kilometres a second in a vacuum, and it can get slow. It can be slower than that. The first seconds after the Big Bang, it expanded billions and billions of kilometres. So presumably, the speed of light is not immutable. The fact is that the speed of light is actually governed by space within space. Space itself can travel almost any speed at all, faster than, and that's a scientific fact, I think you'll agree. The speed of light can be exceeded by the expansion of space itself, but not within space. That is it. And just one last point is that if we predict the universe going on and on forever, yet 96–97% of the universe is dark matter and dark energy. We don't even know what that is. So how the hell can we know what its outcome will be?
Okay. Now, as regards the universe expanding faster than the speed of light, the limitation of the speed of light only applies to measurements, which can only be done where you are or where you have instruments. So if I say that the 40 billion light years away, the stars are receding at faster than the speed of light, that doesn't violate any law. So the speed of light limitation is only a local effect, and the expansion of the universe doesn't violate it.
No, I agree. There's one few that agree with that.
Yeah.
And regarding dark percentage, dark matter.
Okay, we'll get on to that.
Yeah.
Dark matter is where's my dark? Dark matter is there's a lot known about it. It's dark energy. Where's dark matter? Lost it. Never mind.
It went dark.
Yeah. Oh, there we are. That was it.
Oh, there's stuff.
Almost.
That's it. Now, how do we make that big again?
F5, I think.
Or this one here. Okay, dark matter. Basically, there is too much gravity in galaxies because from the rotation of the galaxy, it's easy to work out from the radius and orbital period what mass is in the centre, the gravitational mass. And there's about 3 times as much mass holding the galaxy together as is accounted for by the visible matter, which is counting the stars and planets and gas. So therefore there must be dark matter in there which we cannot see but which is attracting all the other matter. Very simple reason. There's got to be something there. Either that or gravity breaks down. But gravity is seen to apply even on bigger scales than that. So gravity doesn't account for it. And by using gravitational lensing in the top picture on the left, that's a picture, that's an actual photograph of some distant stars, and those streaks are lensed objects. They're remote galaxies that have been lensed by something in between, and by measuring that lensing on a computer, they can work out the physical distribution of the dark matter. And that's done in the diagram on the bottom left. And they can work out a distribution of the dark matter. And the picture on the bottom right represents the physical distribution of dark matter in a particular galaxy as revealed by lensing, and you can see that it's in the galaxy but it's not uniform. And the picture on the bottom left is where there's been a collision of 2 galaxies, and the 2 galaxies have passed through each other without interference. They're the visible stars, because the stars are so tiny compared to the gap between them that 2 galaxies can go through each other and only a tiny fraction of the stars will collide with one another. Most will go through untouched. And However, the dark, and in fact the gas, so you can see the dots are the visible stars, the red blotches are the gas in, now the blue blotch is the gas from the stars, from the two galaxies, and that shows that when the galaxies collided, the gas collided with the gas and formed one single body. So gas collides with gas, stars don't collide with stars, and when they do the lensing tests on that, that gives you the red blotches, and they find that the dark matter has passed through itself and come out and is still at the centre of each galaxy. So basically this galaxy will continue on much as it was before, with the orbits of a few stars changed, but minus its gas. There's gas left in the middle. So this shows that dark matter still remains inside the galaxy and doesn't collide with itself, doesn't interact with itself very much. So there's quite a lot known about it.
There's no such thing as empty space, is there?
Well, there's no dark matter between galaxies, it's only within galaxies.
There's no such thing as nothing.
Now dark energy, on the other hand, is an entirely different thing and is much less known about it. And it's to explain the expansion of the universe. I'm not going to describe this equation to you in detail, but in case some of you recognise it, that term there, lambda, which is Einstein's cosmological constant, they call dark energy. They don't know what it is, but it's either physical energy in the universe that's causing it to expand, or it's simply a constant that arose through nature. So that's, I think that answers all three of your questions.
Okay.
To the extent that it's known.
Okay. Abby?
All right. So my question, I think there are two parts to the question. The first part is regarding the free will and destiny and whether everything is preordained in the universe.
Yeah.
Given conservation of energy, shouldn't that logically be the case, that everything will follow set path, except we obviously cannot figure out what's going to happen? And secondly, any thoughts on the holographic principle?
Any what?
Thoughts on the holographic principle?
The holographic principle, okay. First I'm going to dismiss that. I don't know much about it, and it's very much a hypothesis at this stage. I thought that applied to black holes. The surface of a black hole contains all the information in it. Is that?
And we're inside a black hole.
And we're inside.
And we're inside it.
Yes.
Okay, I'm going to say I don't know. That's one I don't know.
Well, we're in another dimension,
And,
don't they?
and what was the first part of the question, Abby?
The conservation of energy in the universe,
Yes,
basically,
okay.
which means
Conservation of energy and momentum are very well understood. I know a lot about them because most of my career in research and teaching has been applying those things in rocket flights in particular. And no, that's the evolution of the universe is not fully determined by those things. It needs other laws as well, or other events. For example, billiard balls. Billiard balls obey conservation of energy, except for losses in the collisions, and conservation of momentum very well. And you can't predict what's going to happen with billiard balls with total certainty, because after many collisions, the uncertainties in the measurements grow to exceed the size of the ball, so you can't predict. So no, conservation of energy and momentum are not sufficient to predict what happens in the universe.
that wasn't the question. And I wasn't just talking about gravitation. I was also referring to the fact that given that everything is a physical process, and if everything started with some initial conditions, then given that it's obeying certain formulae, such as the one you've got on the board, every moment of time that follows should be a function of the previous moment of time. And so essentially that rules out free will entirely, because everything in the universe has to unfold in a certain way.
Okay, well, yes, that.
But not if you go with quantum mechanics.
Yes.
Quantum mechanics.
Yes. Two answers there. Quantum mechanics appears to include genuine chance. Okay, uncertainty, yes. Except for that de Broglie-Bohm principle that I mentioned, which is not proven, and that's enough to prevent prediction of what would happen in the future. However, the brain doesn't work by quantum mechanics. Strangely enough, each axon and neuron in the brain contains billions of atoms, so quantum uncertainties don't apply. So the brain can be regarded as a classical device, and hence it could be deterministic over a given period of time. For example, if you were able to scan a brain completely and put that into a computer, build a computer to match the brain, the current theory would be that that brain would exactly reflect the choices that person would make, to the extent that it was a high fidelity model. So there's an element of determinism there. And you say it rules out free will. Well, my definition of free will is that it's the feeling we have while the brain is making a decision. So I've redefined free will, in other words, into something that works. So does that answer your question about free will?
Yeah.
Yes.
You determine that, haven't you?
John.
Okay, let's see, I suppose you were talking about the edge of the universe, just something incidental. I'm reminded of Johnny Harp, that when somebody said that they were going off in search of the world's edge, the comment was, take care you don't cut yourself. So anyway, but let's see, a few things. You were talking about free will and determinism. I mean, this may be a technical difference, but I see the difference between determinism and predictability. So you might say that the universe is determined, but you can't predict it. Because like basically prediction is when something has some sort of pattern to the movement. Let's say planet Earth rotating around the sun. You can know what it'll be in like 20 years' time without actually having to, as it were, crank through the whole system to find out where it is in 20 years' time. So there's a difference between things being determined and things being predictable. Because when they're predictable, it means you're simplifying the thing somewhat so that you can do that. So I suppose you're also talking about the nature of the universe. I think those are the two things that I remember. I probably thought of one more thing, but I can't remember.
Well, I'll address some of those things. Chaos theory. The chaotic system is actually deterministic. And that if, in principle, if you knew the location and velocity of every particle at the beginning, you could work out what it would be doing forevermore. Think of the weather.
By cranking through it, though.
By cranking through the calculation. If you'd need a computer bigger than the universe, but in principle, you could do that. So even chaos, we think of chaos as introducing chance, but a chaotic system is strictly speaking deterministic. Now John says it's not computable or predictable.
Not predictable, yes.
Because to do so you would need infinitely fine measurements, and no engineer or scientist can ever take a measurement that's infinitely fine. You need an infinite number of decimal places to define it. So therefore, even if it was determined, we could never tell because we could never predict it very far in advance.
After the prediction, we just can't do it.
Yes.
Ian, I just wondered, could you put that picture up with the beginning of the universe so I can explain this a little bit better?
The beginning of the universe?
Yeah, the one where we had the... yes, this one. This one, very good. Now, I just want to say, when I first met you, I was sort of like, say, 70% religion and 30% science. Lately, since I've known you the last year or so, or few years, I've now gone probably, 80% science and maybe, 10% religion and 10% I don't know. But
yeah.
So you have been an influence on me. I just want to let you know that. But look, getting back to this singularity here, this Big Bang. Different people say different things. Some people say it was like the size of a room, or size of a. Was it just a minute sort of just speck? Is that what they're saying?
No.
Was it the size of a planet, maybe?
Okay, we have to distinguish things here. That the universe is believed to be infinite, most likely. Meaning, no matter how many stars you label, there'd still be ones you hadn't labelled, and we don't even need that. What we need to know is it's got no edge. No matter how far you travel, you won't reach an edge and you could keep going.
Okay.
And that applies even at the Big Bang. So the Big Bang happened everywhere. So you can't, what you can say is the visible universe today is 13.7 billion years across, because that's not limited by the size of the universe, that's limited by the amount of time it's got for light to reach us from there. So when we talk about the size of the universe, most scientists mean the size of what is now the visible universe. Imagine that you could define some stars at the edge. They would lie on the edge of a sphere, 13.7 light years in diameter. And imagine those stars to be labelled, and you can track them back through the Big Bang, and maybe 1 second after the Big Bang, that might have been a metre across or something, I don't know the figure.
Okay.
But that wouldn't stop the fact that if you were able to travel outwards, you would read more and more matter the further you went. So the universe wasn't a metre across. Today's visible universe was a metre across.
Okay.
And even a trillionth of a second after the Big Bang, the universe still had no limit. So it was still infinite in extent.
But all that was compressed in, like all that, all them stars, all them planets, everything was compressed in of the known universe that we
Yes.
can see. And it was compressed into, say, a metre, for example.
That's maybe a second after the Big Bang. But earlier still, it was smaller still, all the way down to a point. Except that physics can't take you all the way down to a point due to the Planck limit.
I think physics can take it down to about the size of a soccer ball.
The soccer ball for the visible universe. Oh, thank you.
At the moment, yeah.
I didn't
And
know
I
that.
think religious people, they look at that and they ask themselves, well, why? What is the point of it? Like, you know what I mean?
Well, does there have to be a point?
You can't help actually thinking that, you know, and I guess...
Yes, you can.
and science says it was, and to me, just the fact of all these planets and all these stars and the size and this new thing, this dark matter and this so-called dark energy we don't even know about, was actually, and again, this is only what we can see. It could be even more further. Was compressed to 1 metre. We assume was one.
Yes.
All that, it must have been pressure to compression, and who made that
Well,
1 metre?
Gareth,
That's
they
the
do
thing
call
too,
it-
you know.
They do call it the Big Bang.
Yeah. You know what I mean? Like it does, the mind boggles, and I think religious people look at that and they say, well, why? What's the point of it? And the other thing that doesn't make sense too, you brought, which I found very interesting. Okay, it exploded initially and was obviously going very super fast. Now scientists have discovered that it's actually starting to speed up, and it's spreading even, and it's escalating. That doesn't make sense. Like when a bomb goes off, like initially it's very fast, you think the bomb slows down. Now,
That's because the bomb's surrounded by atmosphere.
that's true in gravity. That you do have a point. Out there's no gravity, no atmosphere. But
Okay.
but still, the initial energy was at a certain speed, whatever that speed was. But something is making it go faster. Now you're saying it's this dark energy, I believe. Is that correct?
Well, they
Excuse
call
my
it dark
ignorance.
energy.
No, it's the space that's going, not
It's
the, not
Einstein's
the energy.
cosmological constant, the lambda here, that does it. And one hypothesis is that is caused by dark energy that we can't see. For example, they've recently discovered the Higgs boson, the Higgs field. But for the Higgs boson to exist, which they've actually seen in particle accelerators, all particles pop out of the field when you apply quantum mechanics. Therefore, there is a Higgs field. And the Higgs field doesn't interact with anything in the universe today, hasn't been since the Big Bang, but it can provide energy in the universe. So therefore it could be the Higgs field or a related field that is providing that expansion, like a pressure in the universe.
Okay.
Okay, Simon and then Tony. I've taken it that you wanted me to go over time. So, after Tony, I'd like to ask a question and then we finish.
My question is about size. With respect to what? Explain with respect to what? 1 metre measured against what? If we've got a universe.
Okay, that's an easy one. The wavelength of light emitted by a hydrogen atom in a particular state. That's how we define length.
If you've got a nothing before the Big Bang, there are only rules. There's no space. Therefore, there's no infinity either. There's absolutely nothing. I mentioned...
Well, there might be something there, we don't know what it was.
Well, at a point, if we're defining a start, a point, before that start, you haven't got anything because that's not the point where it started. But, you know, by definition, this is just a logical thought process. At that point, if there were no rules, there's nothing to stop absolutely everything occurring. Once everything has occurred, it's self-constructing. It will generate its own set of rules.
Not
And we
quite.
have lots and lots of different rules, many worlds, as I mentioned earlier.
Yeah, Okay. I would say that whatever existed before the Bang, before the Big Bang, must have given rise to this universe. And that's a pretty prescriptive thing. You could rule out many theories on the grounds that they wouldn't have given rise to us.
Well, indeed, but in the many worlds theory, one of those did give rise to us, and the other ones didn't.
Now, there's several many worlds theories. There's,
Indeed.
Parallel universe.
there's the parallel universes
It's
theory,
10 to the 500, yes.
and there's the many worlds interpretation of quantum mechanics, which is not related. So I think that's out of our scope for today, and
Okay,
out of my
Tony.
knowledge too.
Oh, well, thank you, Ian. It's very good. I just want to putting it real simply, of course, the issues of relativity. Now, just quickly with the Higgs boson, I just wonder, can you answer this? Is this correct that it took a trillion examples to test whether this particle exists before it was discovered, and if so, why did it have to take a trillion tests?
Okay, well that's a topic for another talk, but I can answer it quite well. They fire the protons at one another at high speed, as you know, and they get many collisions, and they produce showers of particles, and they measure billions of collisions every second, and they select those of a particular type. And most of the particles that come out, in particular pairs of photons, they have a spectrum. If you have a filament light globe that's glowing, it produces a continuous spectrum of light. Do you understand that? And you could draw the spectrum as an intensity versus wavelength that might have a curve like that, say. Intensity versus energy, we'll say, frequency. Now, if there's no Higgs boson, there'll be a uniform spectrum. So what is, they took their trillions and trillions of measurements and took the spectrum of it, and they found out that the spectrum has a bump in it. I do have a slide of that, but it would take me 5 minutes to find on the computer, so I'll do it later if you want to. And that bump in the spectrum it tells you that there's a particular event which is producing photons whose total energy is 125 GeV. And that is not a uniform spectrum. Now it's true that they discovered about only 300 excess events out of trillions and trillions of events that gave this bump. So what that means is you can't point to any one collision and say this was due to a Higgs boson. What you can say is that 300 of those trillion collisions are not accountable by the uniform spectrum. And that's how they found the Higgs boson. So that's about as vague and tenuous as you can get. So to make that into valid science is quite an art, and that's why it took, what was it, 6,000 people and X billion dollars to do so. So it's a blip in the spectrum. And I have a poem. If you want to learn more about that, go to YouTube and look up Ode to the Higgs. And there's a poem and a song related
I've seen it.
that explains that.
Very impressive.
Yeah.
Thank you, very good.
Okay, I'd like to ask or say something. When you were speaking about the brain and how it works, when I was doing my PhD, I went and interviewed in the United States and in Europe, and then when I got all my information and prepared everything, it took me 10 months to work out in my mind's eye how I was going to write a thesis, a doctorate. And I let it go, and I kept thinking and thinking while I did other things with the Humanist Society. And then all of a sudden, in my mind's eye, I saw it. Now, recently I went down to one of our humanists who's in a retirement home, Bruce Barry. He's got dementia, and I photographed him because I want to paint him and put it in the Archibald Prize next year. So I took photos, got my canvas, I've already got paints, and in my mind's eye, I was thinking of something that would do it justice to go in the Archibald Prize. And then all of a sudden, I saw it in my mind's eye. So what is that when your brain is doing that? That's all the work.
Okay, well, I go to the fundamental level and say it's electrochemical processes in the brain governed by the four forces of nature. As to the higher levels of the process, I don't know, and I don't think anyone knows at this stage. So,
because inspiration, I mean, that's what I wait for.
well, we say that it's quite clear that the brain has many conscious processes. If you read Daniel Dennett's book, Consciousness Explained, he goes into that in some detail, and he says that different parts of the brain are carrying on with calculations and estimations all the time that we're not aware of, and it's only when they converge to a certain critical mass that it pops into consciousness. So it could be that your brain was processing these things for the 10 months and you were only aware of the tip of that iceberg thoughts. So that's my understanding.
Now it's been like 2 months, and there I saw which of the, how I was going to paint him, with what sort of background that would be worthy. I mean, I don't know that I could stand a chance, but that would be worthy for me, because you have to have a celebrity. And I thought that would be really good for because he's a humanist celebrity, So, thank you. I think we need to wind up now. Thanks everybody, and let's give a warm applause to Ian. He was very